Okay then, so today we are going to do a little bit of practice on sketching surfaces, okay? That's gonna be at least the first part of this review. Okay. So I want to start by looking at sort of a simple example. So let's consider the equation z equals x squared plus y squared. And we want to sketch the surface that is described by this equation, okay? Maybe first, do you guys have an idea of what the surface is going to look like? Maybe you guys already know it. Okay, so in order to sketch a surface, there's a couple of techniques that we have to try to visualize it. One technique that we have is sketching level curves. Okay, so let's see how this technique works, all right? So in the equation that we have right now, z equals x squared plus y squared, let's choose a couple of values of z and let's plug it into this equation and let's see what that looks like. So let's say if I plug in z equals 1 into the equation, we're going to get x squared plus y squared equals 1, okay? All right, so x squared plus y squared equals 1. What kind of figure does that equation represent? Yeah, so it'll be a circle. The radius would be? Yep. Yeah, so it's a circle. R equals 1. Okay. So let me try to draw this level curve right now. So what this is telling us is that at a height of z equal to 1, let's say that up here is a height of 1, that on our surface there's going to be like a circle of radius 1 at this height. So I'll try to draw that in the picture. Okay. All right, so imagine this is a circle of radius 1 that's at a height level of z equals 1, okay? So this is a part of the surface. It's the part of the surface at this height of z equals 1. If I try plugging in maybe 1 or 2 more values of z, what if I go up to z equals 4, okay? Then we would get the equation x squared plus y squared equal to 4. So what would that equation represent?
A circle of radius 2.
Yeah, good. Circle radius is 2. So this is saying if I go up to a height z equals 4, so maybe about here in the picture, that there should be a circle of radius 2 this time at this height. And you can kind of see as z gets larger and larger, what's going to happen is we're going to keep getting circles of larger and larger radii, okay? Maybe, I might just maybe note, if we plug in z equals 0, we get the equation x squared plus y squared equals 0. All right, what would that be? Yeah, you can think of it as like a circle of radius 0. But this is basically just going to represent the origin then. So the only solution is if x is 0 and y is 0. Yeah, so if you try to connect all of these level curves together, that gives you some idea of what your surface will look like. So in this example, the surface is what we call a paraboloid. Okay? All right. And so then the reason why we call these level curves is because these are curves on a surface, but they're all like different heights or different levels. Okay. All right. Any questions about that? Yes.
Would it be called an elliptic parabola?
Okay, yeah, that's a good question. So this would be, I guess, a circular paraboloid because the level curves are all circles. If
How do you know if it's not a cone though?
Yeah, I'm going to actually do that as my next example, so I want to touch on that, okay? But maybe before that, since someone is asking about circular versus elliptic. So if I modified the original equation by putting some constants in front of the x squared and the y squared. So now what's going to happen is it's still going to be a paraboloid, but your level curves are going to be elliptical. So let's just say, as an example, when z equals 1, this equation, because it's not quite symmetric anymore, it's going to represent an ellipse. And it's going to turn out to be a paraboloid, but the level curves are ellipses. So it will be an elliptic paraboloid. Okay. All right. Any questions about that? All right. Good. Yeah. So I want to do an example of a cone now, and okay. So let's look at this equation. I'm going to do z equals the square root of x squared plus y squared. Okay. All right. So we're going to do kind of the same thing, look at a couple of level curves, try to visualize this surface. All right, so if I do maybe like z equals 1, as we did before. Okay, so here the equation becomes square root x squared plus y squared equals 1. All right, and if we square both sides, it's just the same as x squared plus y squared equals 1. All right. So that gives us a circle of radius 1. And that's going to be at a height of z equals 1. Okay, so we kind of have something similar to start with. At that level curve, a circle of radius 1. At the level or height, z equals 1. Now if I plug in z equals 2, okay, then we're going to get the equation square root of x squared plus y squared equals 2, which after squaring both sides will be the same as x squared plus y squared equals 4. Okay. So this time we get the circle of radius 2 at a height of z equals 2. Okay. So if I go up to the height of z equals 2, I have a circle of radius 2 now. And you can see it's very similar to the paraboloid. So as you go up, as z increases, basically the radius is going to be increasing. So then the question is, how can we maybe distinguish this being a paraboloid versus like a cone or something else? Okay. So what I've been doing so far is I've been sketching level curves, which I get by plugging in numbers for z. What you can also do is plug in numbers for the other variables. So plug in like a number for x, or plug in a number for y. So when you do that, you'll be getting like other curves that are on the surface. So you can try to use those to get a better picture of it. Okay, so when we plug in values for other variables, I think we call the resulting curves traces. I think we don't call them level curves because they're not like increasing in height along the z-axis, so we call them something different, and we seem to call them traces. Okay. But for instance, like instead of plugging in a number for x, let's plug in. Instead of plugging in a number for z, let's plug in a number for x. So as an example, let's just try x equals 0. Okay. So our equation was z equals the square root of x squared plus y squared. So in this equation, it's z equals the square root of y squared. And what is the square root of y squared equal to? Plus or minus y. Okay, good. So formally, you can write it as 1 by saying it's equal to the absolute value of y. Okay. Okay. So let's think about what this means in our picture. Let me see if I can. I'm going to try to zoom out a bit. Cool. Okay, so x equals 0. This corresponds to the yz plane, all right, when x equals 0. So when we look at this trace where x equals 0, we're looking at the part of the surface which is in the yz plane, all right? And in the yz plane, what we have is this equation z equals absolute value of y. Do you guys remember what the absolute value graph looks like? A V shape, yeah. So the yz plane, it should look something like this. Okay. So in my picture, so here in the yz plane, we have sort of like the profile, the trace of an absolute value graph, so like a V shape. Okay. So it's really this that kind of helps us to see that the resulting surface will be a cone as opposed to a paraboloid, okay? Yeah, so if you're not too sure, looking at different traces will give you a better idea of what the figure will look like, okay? All right, is everyone good with that? Okay. So actually, if I go back to the first example with the paraboloid, let's just look at one of the traces to get a better sense for what's going on. Let me just do the x equals 0 trace again. Okay? So for the paraboloid with the equation z equals x squared plus y squared, when x equals 0, it just becomes z equals y squared. So this shows us that in the yz plane, we're going to have sort of the profile of not an absolute value, but a parabola, z equals y squared. Okay. And so that's how you can see that the profile is going to be more parabolic in shape as opposed to more of a V shape, like from a cone. Okay? All right, is that good? Yes.
Would the cone have a mirror image like?
Yes, okay. Funny because I was going to do that next, all right? So this is very good. Yeah, so right now in this equation, I had z equals square root if I make a small modification to that, so what I'm going to do is I'm going to take this equation and I'm just going to square both sides. So we're going to get the equation z squared equals x squared plus y squared. Okay? All right. Okay, so since all I did was square both sides of this equation, you might think that this is basically going to be the same, because it's basically the same equation, right? Okay. There's a small difference though. So in this example, notice that we have specifically that z is like a positive square root. So that means that there's only going to be positive values of z in this surface. So hence we only have like something that's above the xy plane where z is larger than 0. But when I square both sides, when we now have z squared equals x squared plus y squared, what's the difference between this and the previous question? The main difference is that in this example, z can also be negative. Okay? So it's really the same as the previous example. Except in the previous example, z had to be the positive square root. But in this one, z could be plus or minus. It could be negative. Okay. So this surface is not going to be like a cone, but it's going to be, I guess, what some people call like a double cone. Okay. But basically, we have the same cone from earlier above the xy plane. But now there's also going to be a mirror image. So when z is negative, we're going to basically get the same thing, but it's going to be going this way instead. Okay. All right, so yeah, this one results in a double cone. All right. Do you guys see the difference between the cone versus the double cone? All right, good. Okay. Any questions about that example? Okay, so in this example of the double cone, if I rearrange the equation, I can write it as x squared plus y squared minus z squared equal to 0, right? So what I would like to do is, again, make a modification to this equation to come up with another example. So let's suppose I modify it now to get the equation x squared plus y squared minus z squared equal to, let's say equal to 1, okay? All right. And so again, we want to sketch the surface being described by this equation. Now, when I'm sketching surfaces, so I try to sketch some level curves or some traces to get a feel for what it looks like. Something that I personally do is I try to look for level curves or traces which are going to be circular or elliptical. Just because circles and ellipses are easy to visualize, easy to draw. So personally, I always look for circles or ellipses when I'm trying to sketch these surfaces. All right. So in this equation, if I just move the z back over, so we get x squared plus y squared is z squared plus 1. X squared plus y squared suggests that you're going to be getting circular level curves. So therefore, I'm going to look at some level curves by plugging in some values of z. Here, let's just start with a z equals 0. So if I do that, we're going to get x squared plus y squared equal to 1. Okay? All right, so we know that's a circle, a radius 1. And this is at the height of z equals 0. All right? So at the height of z equals 0, that's going to put us in the xy plane. So in the xy plane, we should have a circle of radius 1. Okay? Okay. Now let's say if I plug in z equals, let's do z equals 1. Yeah, so when z equals 1, we get the equation x squared plus y squared equal to 2. All right. So again, it's a circle. This time the radius will be, what's going to be the radius of the circle? Yeah, square root of 2. So don't forget to square root to get the radius, all right? So you can kind of see what's going to be happening. This is similar to the examples that we've seen so far. What happens is as z gets larger, basically the radius of the circle will be getting bigger. So let's say up here at the height of z equals 1, we have a circle of a slightly larger radius. Okay. Now notice that because in the equation we have z squared, notice that we will get the same thing when z is plus or minus 1. Okay? So that means there's going to be some symmetry to our surface. So as z equals negative 1, you're going to have the exact same circular level curve. Okay? So if I just try to connect these circles to just get a rough sketch, we're going to get a figure that will look something like this. Okay? And then it'll kind of keep going up more, getting wider as it goes along. Okay. So this surface, I believe they call it a one-sheeted hyperboloid. All right. And then to see why we call it a hyperboloid, if I look at the x equals 0 case, so if we plug in 0 into this equation, you're going to get y squared minus z squared equal to 1. And you guys might be familiar with this type of equation, but it's the equation of a hyperbola. Okay. So in the yz plane, this hyperbola will look like something like this. Okay? So then you can kind of see that profile of the hyperbola in the picture here and here. And because you have those hyperbola traces, that's what we call it a hyperboloid. Okay? All right, questions? Are we good? Okay, let's do one more example. So this equation gave us that one-sheeted hyperboloid. Again, I'm going to take this equation and make a small modification to it. well, maybe I'll do two modifications. So let's say instead of being equal to 1, I'm going to make it equal to -1. And maybe just because to make it a little bit more interesting, instead of doing plus y squared minus z squared, let me change it a little. Let's do minus y squared and plus z squared instead. Okay? All right, let's see what that affects. Okay, so again, as I was saying earlier, I look for circular or elliptical. Level curves or surfaces, or traces. Look for circular or elliptical level curves / traces. So this time in my equation, in order to get circles, I will get circles if I have like x squared plus z squared equal to something. So that would suggest that in this equation, I would like to move the y squared over. So we have the equation x squared plus z squared equals y squared minus 1. All right. So what I'll be doing here is I'm going to be plugging in different values for y this time. And we'll be seeing how that will affect the radius of our circles. Okay?
Doesn't matter which variable you put that side?
Well, so it doesn't matter, but as I was saying, I try to get circles or ellipses.
Okay.
So, like if I move the z over, I'd have x squared minus y squared equals something. And x squared minus y squared equal to a constant, that's like a hyperbola. So I moved the y squared over because x squared plus z squared equal to a constant, that gives me circles. Okay. All right. Yeah, so it's better to try to draw circles versus hyperbolas. So that's why I always try to do circles. Sorry. Okay, so let's try to plug in a couple of values of y and let's see what happens. Let's consider what happens when we plug in y equals 0. So when y equals 0, we're going to get the equation x squared plus z squared equal to -1. Okay? So what does that equation represent? Yeah? Is something confusing about the equation perhaps? Okay. Yeah, so normally when you have the x squared plus z squared equal to a constant, that's a circle of a certain radius. Here, what's the problem? What is the radius? What would the radius be if you try to compute it maybe? Yeah, so it kind of looks like it wouldn't exist because you'd be trying to do x squared to -1. So what's happening in this equation is there's actually no solution to this equation. It's not possible. So a good way to see it is notice that on the left-hand side, since we have x squared plus z squared, that's always going to be non-negative because everything is getting squared. So it's not possible that it will be equal to something that is negative. Okay. So in other words, there's no solution to this equation. What does that say about our surface that we're trying to sketch? Okay. Well, we're not getting any curve when y equals 0. So that means that there is no y equals 0 trace, if you will, to our surface. All right, so that's maybe kind of interesting, all right? So let's see here. So in order to get something, let's look at y equals 1 first, all right? So when y equals 1, now we get x squared plus z squared equal to 0. And what would that be? And so if we have x squared plus z squared equals 0, what kind of figure or curve would that represent? So we saw an example of this earlier, right? You can think of it as a circle of radius 0. So in other words, it's just going to be a point, right? So x squared plus z squared can equal 0 only if x and z themselves are 0. Okay. All right, but notice that we are also at a specific y value of y equal to 1. So what this is telling us is that when y equals 1 over here, x and z are equal to 0, which will give us that point right there along the y-axis. Okay? Okay, so we found a point on our surface. Again, notice that since y is getting squared, we have a certain symmetry so that whether we do positive or negative values, we're going to get the same thing. So that means that when y is negative 1, we're also going to have a point on our surface. Okay? All right, good. Now let's see what happens if we just maybe choose more about y values. Let's go up to y equals 2, all right? Whether it's plus or minus 2. Our equation, if we plug in plus or minus 2 for y, so get x squared plus z squared is 4, 2 squared is 4, minus 1 is 3. Okay. So that gives us the equation of a circle. Radius would be square root of 3 this time. Okay. Okay, so what is this saying? So in my picture, if I go out to like where y is equal to 2, so at this y value, there should be a circle of radius square root of 3 along like the x and z direction, so parallel to the xz plane. So I'll try to draw that. So a circle, I'm trying to draw it so that's parallel to the xz plane. And it's like along this y value at y equal to 2. Okay? And we had the exact same thing for y equals negative 2. So if I go out here, where y is negative 2, we should have kind of the same figure. So I'm going to try to draw it. Well, that's pretty good, I suppose, all right. Okay, and then as y gets larger, as y keeps getting bigger, the only thing that's going to do is give us circles of larger radii. So that means the pattern will sort of persist, and you're going to get more larger circles as you go further and further out. So if we try to connect everything together, you'll get a figure looking like this. something like that. Yeah, so as you go further out along the y-axis, the circles get bigger, so it's something like this. And earlier how we noted that like when y equals 0, there was nothing. So that's why you can kind of see in the picture there's like a gap in between these two things, if you will, okay? So this kind of surface, we call it a two-sheeted hyperboloid. Okay? Alright, so you guys can see why it's called a two-sheeted hyperboloid this time, right? Because there's kind of like a two sheets, one here and then one here. Okay? Alright, any questions about that? Okay. Alright, so those are all the examples of sketching surfaces that I wanted to do. I might recommend you guys maybe look at a saddle surface. I am very bad at drawing saddles, so I'm not going to do that because I don't want to like record myself, trying to sketch it. But maybe look up what a saddle surface looks like. Look at the equation and what it looks like. There might be some like videos on like how to sketch a saddle surface as well online. I should have looked that up actually, but I didn't think about it. Okay. All right, so those are just some examples of sketching surfaces. I want to do a little bit. Yes, did you have a question?
So I was told by my
Mhm.
problem set leader,
Sure.
the TA, he said that while we're drawing it, that when we do the exam, we need to put a couple of the points on there. Is that true? Or?
I guess that's something that you should clarify with your TA or your instructor. So regarding like what points to be sketching, like maybe just like some points like these 2 points which are maybe notable. Or I'm not sure if you're thinking about sketching curves and you might want to sketch some points on the curve. Okay? So I think when you're sketching surfaces, it would maybe prefer to see level curves or traces. You might be thinking about sketching curves in which you might want to see some points on the curve. Okay? All right. Okay, so speaking of which, I did want to turn now to curves. Maybe some examples of trying to visualize and sketch them. I'm going to open up a new window, I think. So instead of looking at surfaces, we are looking at curves. So I want to recall very quickly a little bit of what we did last time regarding lines. Okay. So remember that one way to describe a line was to use what we call a parameterization. And for lines, they had a specific form where the parameterization RT had the form like R0 plus TB, where R0 was a point on the line and V was a direction vector. So you guys remember this stuff? All right, good. Yeah, so this is a point on the line. And then V was a vector pointing in the same direction as the line. We just called it a direction vector. Okay, so in terms of the components of R0 and V, you could also write this in terms of the x, y, z coordinates. It would be like x0 plus at, y0 plus bt, z naught plus ct. And then these gave us like sort of like the parametric equations for a line. You guys remember that? Okay. So if we sort of generalize this, so let's suppose we have like some function r of t, which will just give us three functions for the x, y, and z component. So not necessarily of this specific form, but could be like x of t, could be t squared, and things like that. So once we make that multiplication, what we're going to get is a parameterization for like more general curves. Okay. So they're not necessarily going to be lines anymore, they'll actually be curvy, all right? So we'll look at maybe some examples to start with. Let's try and do an example that will it will be kind of familiar to us. So let's consider this parameterization of a curve. So r of t is going to be 2 cosine t, 1, 2 sine t, okay? And we want to maybe try to sketch the curve described by this parameterization. So maybe first, can you guys already tell maybe what this curve is going to look like?
It is circle.
Okay, what would the radius be? Okay, and where would it be located?
The origin.
Well, you're close, all right. Why did you think it was a circle?
Because cosine and sine.
Yeah, okay. So let's look at this for a moment. So if I write out like the parametric equations, you have that x is 2 cosine t, z is 2 sine t. We do also have a y equal to 1, so y is constant, all right? Okay, so if we just focus on x and z right now, that kind of looks like the equations for like polar coordinates, if you guys remember that. Like x is r cosine theta, z is like r sine theta this time, if you will. Okay. Here, what would the value of r be in our equations for x and z? Yeah. So if r is 2, then that would suggest that you have a circle of radius 2. Okay.
How do you know the radius was 2? Because
Yeah, coming from the coefficient. So remember, like in polar coordinates, if x is r cosine theta, so r would have been the coefficient.
what if there wasn't 2 over there? Would it be 0? The radius?
If there were no 2 at all,
Uh-huh.
there would be a 1 in front, like 1 times cosine, 1 times sine,
So
yeah.
the radius would be 1.
In that case, yeah, okay. Now, another way you can see that it's a circle of radius 2, though, is think about if you do like x squared plus z squared. All right, so like if you square x, it's 4 cosine squared, right? If you square z, it's going to be 4 sine squared. And if you factor out a 4, you'll get, cosine squared plus sine squared. Oops, back to that before. And you guys should remember what was cosine squared plus sine squared equal to? Yeah. So you get x plus z squared equals 4, and that's how you can kind of see that circle of radius 2, okay? Now, however, though, we have y equal to 1, so what does that tell us? Okay, so let's see here. Here's y equal to 1, for instance, okay? So x squared plus z squared equals 4, that would kind of be a circle in the xz plane. However, we're not in the xz plane, we're at the y value, y equal to 1. So that means we should be somewhere out here instead of out here in the xz plane where y is 0. So that means that this curve is going to be a circle of radius 2, but located in the y equal to 1 plane, if you will. Okay. So imagine this being like parallel to the xz plane, all right? So that would be what this curve will look like. So when you see cosine and sine, that kind of helps you if you try to look for like a circle in the equation, okay? Any questions about that? Okay, so I'm going to make a modification to this example. Maybe 2 modifications. So let me change the 2. So I'm going to maybe do 2 cosine t. Maybe for z, I'll change the 2 to a 3. So 3 sine t. The other thing I would like to modify is instead of letting y equal to 1, I'm going to have y equal to t. Okay? So let's see how those modifications are going to affect the picture. Okay, so if I write out the parametric equations, so we have x and z having the cosine and the sine in them. This time we have y equal to t, all right? So let's focus on the x and the z again first, okay? So what's happening now if we have cosine and sine but a different coefficient in front? What kind of figure is that going to be? Yeah, it's not symmetric anymore, so it's not going to be circular. This is going to give us a more elliptical figure. Okay? So one way to see what the ellipse will look like. Okay, so something that I like to do when I have ellipses, if I want to get like the equation of the ellipse, I'm going to take my equations for x and z, and what I'm going to do is I'm going to divide the coefficients to the other side to solve for cosine and sine. Okay? So the reason why I did that is because I want to use the equation cosine squared plus sine squared equals 1. Okay? So if I substitute cosine t is x over 2, then cosine squared would be x squared over 4, squaring everything. Similarly, sine is z over 3, so sine squared would be z squared over 9. That equals 1. And so then you got recognize this as the equation of an ellipse. Okay? equation of an ellipse in the xz plane. If I were to sketch this ellipse in the xz plane right now, so the way it works is, if I like to sketch an ellipse, I like to do that by finding the intercepts. Okay. So notice, for instance, like when x is 0, z would have to be plus or minus 3. So that gives me my z-intercepts at plus and minus 3. If, say, when z is 0, x would be plus or minus 2 to get equal to 1. So that gives me my x-intercepts. When z is 0, x is plus or minus 2. So you kind of get this ellipse. All right. So if you notice kind of what happened though, so basically like the radius in the x direction is 2. Or if you will, like I'll call it the x radius, I guess, is 2. The radius along the z direction, or the z radius, if you will, was equal to 3. So you can kind of, you could have gotten that straight from these equations to begin with. If you're thinking like polar coordinates, r cosine, r sine, for x the r was 2, for z the r was 3. So you can kind of infer that from those equations themselves. Okay. So then that way, like if you notice that right away, you maybe don't necessarily need to go through everything that I did here. Okay. Okay, so we have looks like we have some ellipses along the xz plane, if you will. But we have y equal to t. So let's think about what that's going to be doing to our figure. So if I ignore y equals to t, if I ignore that equation right now, so the x and z equations give us an ellipse. To trace out the entire ellipse, t would have to vary from like 0 to 2 pi, so like 1 revolution, to get like one whole ellipse, all right? Now, however, though, so thinking of t as like the angle, what's happening is as we move along the ellipse, as the angle increases, the value of y is increasing as well, okay? So try to maybe imagine this ellipse here, but as I go further out, as I increase the angle, I'm going to be like moving along the y-axis because the y is changing in value. Okay. I'm going to close the door real quick. All right. So if you can maybe imagine in this picture, if you imagine the y-axis coming out of the screen, as the angle increases, try to imagine like lifting your pen, like having the pen reach out of the screen as I'm tracing the ellipse. So it's kind of like winding outwards, if you will. That's kind of the picture that you would get. So if I try to draw that picture here, so imagine I'm going to try to draw an ellipse along the xz plane. But as I'm winding around the ellipse, I want to be increasing in y value because y is going to be increasing as the angle increases. So I'm going to get a figure that will look something like this. I'm trying to wind around the ellipse, but as I do so, my y is increasing. Okay, that's a rough sketch, maybe not super great, but it's going to have this sort of like a helical shape to it, all right? Kind of going along like this, and then like that. Okay, can you guys kind of see what I'm talking about? Yeah, so it's just like I want to draw an ellipse, but I want to be moving outward along the y-axis. Because as my angle is changing, my y is changing with it. Okay? All right, any questions about that one?
To know which way you're going, you just have to put numbers in.
Yeah, so if you want to get a better sense for the direction, so here I kind of figured the direction out just from like polar coordinates having like a natural orientation to it. But if you're for like a more unfamiliar curve, certainly, the best way to figure out the orientation is to plot some points specifically. So let's just say as an example, I'm going to plug in like 2 points. If I plug in 0 for t, so cosine of 0 is 1. So I'm going to get x is 2. T is 0, so that just means y is 0. And then sine of 0 is 0, so you're going to get this point to start with. Okay? So that would be kind of corresponding to this point here. When t is 0, we're at the point 2, 0, 0 along the x-axis. Let's just maybe plot one more point. A good value to plug in perhaps would be like pi over 2 for the next value. Okay? Yeah, so I'm choosing to plug in pi over 2 because cosine of pi over 2 would be 0. T is pi over 2. And sine of pi over 2 is 1. Yeah, so it's a nice point, if you will. So let's see what this says. So when y is pi over 2, so I'll just kind of guesstimate pi over 2 for y out here. I should be at the point x equals 0, and z should be equal to 3. So this is like, imagine like where x is 0, y is pi over 2, and z is 3. Okay? And so at t equals 0, we're at this point, and at t equal to pi over 2, we're at this point. And then that kind of keys you in on the direction being this way then. Okay? All right, good. Any questions about that? Okay, all right. Let's try to do one more example. I was sketching a curve first. Okay, so you don't always get like circles or ellipses, right? So let's look at another one. Not super crazy, but I'm gonna do this. All right, and let's try to sketch this curve. So no cosines or sines, so it's not going to really have any sort of circular or elliptical shape to it. All right. I like to write out the parametric equations. Sometimes I might see something when I write them out. Okay, so a couple noteworthy things about these parametric equations. Maybe the first noteworthy thing that I see, I think this is most noteworthy to me, x and z are the same, right? We have x is equal to z. All right. So that doesn't give me a complete picture of the curve. That gives me some idea of what the curve will sort of look like, okay? Okay, now in the xz plane, so this is kind of like y equals x, except in the xz plane. So you guys know that it's going to look like a line straight down the middle like that, okay? All right. So I'm going to draw that line in my picture right now. So imagine this is like the line z equals x in the xy plane, okay? All right. Yeah, okay. Now, this is in the xz plane where y is equal to 0, okay? I know that y is not going to be equal to 0, so y is going to be varying. So I know that if I sort of take this line and I stretch it along the y direction, so that's going to give me a plane, if you will. So you guys can imagine this plane here. Taking that line x equals z in the xz plane, and I'm kind of stretching it out in the y direction. Not the best picture. Let me try to make that more parallel. Okay. So I have this plane, and one thing that we can get from the equation x equals z is that our curve should be somewhere on this plane, okay? All right. Now, if we really want to get a better feel, though, for what this is going to look like, then of course I need to look at the equation for y. All right, so we have y equal to t squared. So let's think about that for a moment. Actually, I'll tell you what. Before I do that, let's also just plot some points right now. I think that's a good way to get a better feeling for what the curve will look like at first. So like when t equals 0, what point are we going to get? Yeah, 0, 0, 0. So we'd be starting at the origin to begin with, all right? Let's do a couple more values. Let's do like r equal to 1 this time. Okay, what point would we get there? Yeah, okay. So one way to sort of think about what might have happened is like, so at the point where x and z, along this line where x and z are 1 and 1, what happens is y is also equal to 1, so that means you need to go out like 1 unit in the y direction. Okay. So we have this point here, 1, 1, 1, if you will. Let's do just one more point. So when t equals to 2, what are we going to get? Yeah, 2, 4, and 2. So then when x and z are at like 2 and 2, y is equal to 4, so I need to go like way out to here or so where y is equal to 4. So if I try to sketch that, well, it's already not very good. It'll look something like this, okay? All right, but so this curve that I'm sketching connecting these points, it's in this plane, it's in the x equals z plane, all right? So the x coordinate always equals the z coordinate. But as x and z increase, what's happening is y is increasing as well. So that's why it's kind of going further out in the y direction as you're kind of going like further up, if you will. Okay? And then we kind of got the orientation when t is 0. T equals 1, t equals 2. So that gives us the orientation is going this way. All right? Okay, any questions about that? All right, good. So I've got time for maybe 1 or 2 examples. Okay, so this time, instead of trying to sketch a curve, this time we're going to be given a curve, and we're going to try to find a parameterization for it. All right? All right, so let's say we want to find a parameterization for the curve of intersection between the following 2 surfaces. Okay, so let's do, it doesn't really matter. I'll do this. Okay, I'll do this instead. Okay, so let's consider this equation, y squared plus z squared equal to 1. And then let's look at the equation x plus y plus z equals, let's do 3. Doesn't really matter. Okay? All right, so first, do you guys recognize what surfaces are being described by these equations? So looking at the first equation, y squared plus z squared equals 1, what kind of surface does that describe? You guys should know this, right? So y squared plus z squared equals 1 represents, okay, it would be a circle if it were just in the yz plane. But if I'm in 3D, what's going to happen?
What's the cylinder?
Cylinder, yeah. So like you have the circle of radius 1 in the yz plane. But in 3D, we also have an x-coordinate, which could be anything, because it doesn't appear in the equation. Yeah, so this equation describes a cylinder of radius 1. It's going to be along the x-axis. So I'll try to draw a rough sketch of this. Yeah, so it's a circle of radius 1 along the x-axis, so something like this. Okay? What about the second equation? What does the second equation represent? You guys should know what this is, I think. Not a line. It's two-dimensional. So the second equation is a plane, right? You guys maybe roughly remember the stated form? Yeah, okay. This is actually the equation of a plane. So I'm not too concerned about sketching this plane accurately. Honestly, I'm just going to draw a plane in my picture, okay? So we can maybe imagine having a plane kind of like slicing through the cylinder. Okay? So not a super great picture, but maybe you guys can visualize it. If you take a cylinder and you kind of slice through it with a plane, what kind of figure are you going to get at their intersection? Can you guys try to visualize that? Say like I'm slicing it with like a plane at a certain angle. So you can maybe imagine it's going to be sort of like an elliptical shape, an ellipse. Okay? Maybe imagine like taking a soda can and just like slicing it at an angle. You're going to get like an ellipse where the plane and the can like intersect each other. All right? So that's what the curve of intersection is referring to. When you're talking about the curve of intersection, it's the ellipse where the plane and the cylinder are intersecting. Okay? All right. Now, as for how to find a parameterization for a curve, so this is actually like a pretty difficult question. So I can maybe just suggest like a few strategies to try. All right. So my first recommendation for coming up with a parameterization is to use cosine and sine if you see like a, sort of something like a circle or an ellipse in your equations. That's sort of my first recommendation. Or if you will, I'll just say like use polar coordinates. Cosines and sines. If you see equation of a circle or an ellipse, okay? All right. So for instance, like in this equation, or in this problem, we have that equation y squared plus z squared equal to 1, okay? So that kind of reminds you of a circle of radius 1. So I might try to use cosine and sine to represent y and z, okay? So polar coordinates, I would like to say like y is r cosine theta, z is r sine theta, perhaps. The radius is 1, so that's why I'm doing like 1 cosine theta, 1 sine theta. So of course you can just write y equals cosine, y equals sine then, okay? So maybe I'll erase the 1s now. Okay. So like these equations take care of the first equation, y squared plus z squared equal to 1, okay? Now, however, I also need an equation for x in order to get a parameterization, right? So the idea is I can solve for x in the second equation, and that will give me my equation over here for x, all right? So notice like from the second equation, you can say x is 3 minus y minus z. What I want to do though is when I do like minus y minus z, I want to plug in these equations for y and z. So I'm trying to express everything in terms of theta. So theta is going to serve as like my t in the parameterization. In other words, theta is my parameter, okay? So this would be like a set of parametric equations for the ellipse, the curve of intersection. Can't spell, okay. Parametric equations. So if you want to write it out in the form of a parameterization, maybe do like r of theta is For x, it's 3 minus cosine minus sine. Y is cosine. Z is sine. Okay? That would be a parameterization for the curve of intersection. Any questions about that? Okay. So, there's more than one right answer to these problems. So this is just like a one answer then to this example, okay? I'm gonna very quickly just do one more example, okay? Same thing, curve of intersection. This time my equations are a little bit more complicated. So there's no circles anywhere, okay? So we can't try to use like polar coordinates to help us out, all right? So I just want to show you like maybe like one more technique for trying to get a parameterization of a curve. This technique is a little bit hard to apply when your equations are complicated, but it's like maybe another common technique to try, okay? So the strategy is to choose one of the variables to be your parameter, all right? So in this problem, I'm going to choose z to be my parameter, so I'm just going to let z equal t. So I just kind of made that up, and now what I need to do then is I need to try to express x and y in terms of t as well, okay? So this one's not too bad. From the second equation, x is 2 plus z squared. And if z is t, then we can say x is 2 plus t squared. All right? And then similar for y, in the first equation, if I solve for y, so we could say that like y cubed is, let's do 1 plus z minus x. Okay, so we have to cube root that to get y. Okay. And so y is the cube root of 1 plus z. So for z, I'm going to plug in t. And then when we have minus x, then I'll replace x with 2 plus t squared. Okay. And that gets me a set of parametric equations for our curve of intersection. So this is a little bit difficult because you have to be able to solve for the other variables, all right? But this is a strategy I would recommend, especially if you don't see any circles or anything like that. Try picking one of your variables to be the parameter, and then try solving for the others in terms of that parameter, okay? All right, that's it. I'm a little bit over time, so I'm gonna stop.